Okay, so today we start a new topic which is called probabilistic method. This is a very powerful method used in combinatorics, often to show existence of certain structures and also to prove bounds for parameters like chromatic number or other parameters, which can be used, which can be proved with the help of probability tools. Okay. So basically, we are going to use some tools from probability theory to show this, and this is known as probabilistic method. One of the most striking uses of this method was initiated by Paul Erdos, and it was in 1945 or 47, something like that. And then onwards, it has become very highly used tool in combinatorics. Whenever the usual methods does not work, people try to obtain good bounds using these tools. So what we are going to do is to just introduce this method with three of the simpler and but still very powerful tools. And for this, we will take a quick review of the tools from the probability theory. Okay. So we look a few notations. So we use omega to denote the sample space, which is a finite set for the time being. So we have this finite set omega, which we call the sample space. Then we have a function p, usually denoted by small p, which takes elements of omega to the interval 0, 1. Okay. And this is a function. And if the summation p of x for every x in omega is equal to 1, then we call omega comma p the tuple a probability space. So in some texts, they will also add one more term like omega comma f comma p, where f is an even space. But for the time being, we will be happy with this. Okay. So we have a probability space, which is basically a finite set together with a probability distribution. It's also called probability distribution. And that is the thing. So for example, you can assume that omega is the set formed by the 6 sides of a dice. Okay. So the sides are numbered 1 or marked with 1, 2, etc. up to 6 dots. Right. Now, if the die is unbiased, which means that all the sides have equal chances of coming up, then we can say that the probability of any side to be up is actually equal to 1 over 6, because there are 6 sides. And if you sum over all the sides, right, for I equal to 1 to 6, probability of I, that is equal to 1, because each side has 1 by 6. There are 6 sides, 6 into 1 by 6. This is equal to 1, right? So here is a probability distribution over the sides of a die, right? So 6-sided dice. So this is the probability space. It's an example of a probability space. Now, one of the main tools that we are going to use is to design a random experiment. So what is a random experiment? It is basically choosing elements of omega at random with some associate probability which is given by the distribution. So P of x is the probability that the term x is going to come out, right? The outcome x is going to come out, and if we are going to choose these elements with precisely this distribution probability, then we say we are doing a random experiment within this probability space. Okay? So we are choosing these outcomes, right, the elements of omega, right, by doing some experiment. For example, you take a dice and toss it, right? So the face with the 3 dots comes up. So that is the outcome. And the probability of this happening is 1/6. Right? Now, a subset of omega is called an event. So E is a subset of omega, then we call E is an event. So an example is again like, when you toss a die, right? We can see that, this number of dots comes up will be 1 to 6. But, we can define our event to be, an even number of dots comes up, right? So it's either 2 or 4 or 6. If that numbers comes up, then, this is our event, right? So this event has happened. So for such an event to happen, then we can ask what is the probability of that event happening, right? Or we can do other things with respect to this event. Now, another example of an event could be like, the outcome is a prime number, right? It's either 2 or 3 or 5, right? Out of 1 to 6. So all these things are events. So it's basically a subset of omega. Now, the probability of an event is basically the sum over all the probabilities of its individual elements. So probability of the event E is summation over all x belonging to E. This is E. I wrote it as A. Should be E. Probability of x, right? So the probability that some element of E is selected. So for each element, what is the probability? Add them together. You get the probability that one of them is selected. For example, in the previous case, we say that the outcome of an outcome is an even number. What is the probability that this happens? So it is 1/6 plus 1/6 plus 1/6, right? So it is 3/6, which is 1/2, right? Out of all the 6 numbers, one of the 3 even numbers comes out. Probability is half. Now, if for every element of omega, right, probability of that element happening, right, that comes as an outcome is precisely the same, right? Then it's 1 by cardinality of omega. Then we say P is a uniform distribution. We said that the probability is also called the probability distribution, right? That function. And if the function has the property that every element is given the same probability, then this distribution is uniform distribution. So this is something that we will often use. So we are going to use this terminology. Now, if A and B are events, right? And if I denote by A bar as the complement of the event, that omega minus A, right? Then probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Okay, one can verify these things very easily from the definitions that we did before. And the probability of A complement is 1 minus probability of A. Right? These things are very easy to see. Probability of A intersection B is at least probability of A minus probability of B complement. Then another thing that you can see is that probability of a union of events is upper bounded by the sum of the probabilities. So this is called the union bound. Okay? So if you take different events like A1 to AN, then the probability at least one of them happening is less than or equal to sum over all the probabilities of each of the events. Right? So these are some notions. And then if you have, let's say, disjoint events, okay, B1, B2, etc., Bm are disjoint events, and if these events form a partition of omega, okay, so omega is a set, so you partition it into different sets, B1 to Bm, each one is a subset of omega, therefore, these are all events, we can say, right? So if we have these disjoint events which partition omega, then probability of any event A can be written as summation of the probabilities of A intersection BI, right? So A is belonging to each of these BIs. If, right, look at the intersection, take that part, take the probability, right, and add, right, for each of them. Right? It's like basically, when they are disjoint, you can add, right? The summation will become, the inequality becomes equality here, right? So if for example, basically what we are saying is that if AIs are disjoint, then the probability of the sum is basically sum of the probabilities, and we can make it in a more polished way here. Okay, so that is a quick review of the necessary tools from the probability theory. Maybe a few more, yeah. Okay, so probability of A given B, it's read as A given B. Okay, so probability of A given B is the probability that the event A occurs given the fact that event B has already occurred. Okay, so right, like for example, you are tossing you are tossing a die, right? And then let us say that the event A is that the outcome is 3. Okay, and let's say event B is that the outcome is an odd number, right? Now I toss a die, right? You don't see what is the outcome, but I tell you that whatever number has come is an odd number, right? Then I ask you what is the probability that it is a 3. So you can see that since this is already even though the probability of 3 occurring in a tossing of a die is 1/6, once I tell you that what has happened is an odd number, then you can immediately say that probability of this is actually 1/3, not 1/6, right? Because it could be any 3 of this, right? Equally likely, right? So each of the 3 would be the same. So then the probability of A given that B has happened is it could be different, right? So this is called the conditional probability. Okay? So probability of A given B is the probability that A happens given that B has happened. Now one can easily show that probability of A given B is actually equal to probability of A intersection B divided by probability of B. Okay? So this can be shown very easily whenever probability of B is not equal to 0. On the other hand, in the other example, I tell you that the outcome is an even number, and what is the probability that it's a 3? Then of course it is 0, right? So because probability of A intersection B is 0, right? Now, yeah. So again, example is a pair dice is thrown, and the outcome is even, right? That is the even B. Probability that it is 4 is probability of A given B is probability of A intersection B by probability of B, which is, what is probability of A intersection B? It is A intersection B is basically 4 itself, right? So 4 is the number which happens in A, and B says that it is an even number, right? So 4 intersection B is again 4 itself. Probability of 4 is 1/6. And what is probability of B? Which is B is that the outcome is an even number, so it is 1/2. So 1/6 by 1/2, which is 1/3. So here we get that probability of A given B is 1/3, right? And probability of B given A on the other hand, right, is different, right? So if 4 has occurred, then of course the outcome must be an even number. So we should get the probability 1, and we are getting it because probability of A intersection B is 1/6, and the probability of A is 1/6 again, right? The probability of B given A is also 1/6 by 1/6, which is 1. Now, suppose two events A and B are there, then we say the events are independent, right? If the occurrence of one does not affect the probability of the occurrence of the other, right? So if occurrence of one of the events does not affect the probability of one of the other, then they are independent, right? For example, probability of what we want is that probability of A given B, right, is actually equal to probability of A itself, right? So then the events are independent. So it should be very clear to you that like we should take note here, because it could be a little intuitive that if the events are disjoint, that does not mean that they are independent, right? Usually you might have an intuitive feeling that okay, two events are disjoint, then they are basically independent, but that is not the case. For example, if I know that event A has happened, its complement, which is disjoint from it, right, would not have happened, right? Event A has happened, then its complement would not. For example, I toss a die, right, and the outcome is an even number. Then of course I know that the complement, which is outcome is an odd number, that event could not have happened, right? So they are basically not independent. What we want is that probability of A intersection B is actually equal to probability of A into probability of B, the product of the probabilities, because of this identity. Probability of A given B is equal to probability of A intersection B by probability of B. So events are independent means that this should happen. Now, again, an example is that if A intersection B is empty, right, if they are disjoint, and probability of A and probability of B are strictly positive, then A and B are never independent. So they are actually dependent, because if probability of A intersection B is empty, and if both are 0, then the conditional probability is going to be definitely different, because it's going to be 0, right? Probability of A given B is going to be A intersection B, which is empty set, therefore probability is 0. So therefore they are actually dependent. They are not independent. So disjoint events are usually always dependent. So therefore, these notions has to be very clear. Now, an event A is said to be mutually independent of the events B1 to Bm. Okay. If probability of A given intersection Ci, where I is in I subset of 1 to m, where Ci is an element of Bi or Bi complement, okay, is actually equal to probability of A, right? So this is this is the definition, but intuitively what we want to see is that the any combination of the events, should not change the occurrence of the probability of A happening, right? So A should be independent of any combination of any subset of the events that we are given, right? So one thing again, which is probably not intuitive, is that it is not sufficient that events are pairwise independent, right? It can happen that you have three events like A, B, C, right? And A and B are independent, A and C are independent, B and C are independent, but A and B and C together are not independent. This confusion happens because often it is the case that pairwise relations sometimes are much more stronger than for example sets can be pairwise. I mean sets can be the intersection of a set of sets could be empty, right? But pairwise they are not disjoint. On the other hand, if you know that sets are pairwise disjoint, their intersection is going to be again empty, right? So therefore, but in this case, it is not like that. So it is possible that we have pairwise independence between the events, but altogether they are not mutually independent. So I will give you an example also. So let us say that we flip a coin 2 times. Okay, so you flip the coin once, then that is the and the second time you again flip, and B1 is the event that the first flip is a head. Okay? So you flip it twice. So first time it happens H, right head, then I call that is the event B1. And event B2 is that the second flip is a head. Right? Now I define event A to be the fact that both flips are the same, right? Both are either head or both are tails. Now, of course, one can verify that A is independent of B1, right? Because if you look at the first head, whether first flip is a head or tail, it does not affect what happens to A, right? Similarly, A is also independent of B2, right? Because the second flip is head also does not affect what happens to A, right? We can verify that probability of A given B1 and probability of A given B2 are actually equal to probability of A itself. Now, yeah. But on the other hand, if you look at probability of A given B1 intersection B2, right? B1 and B2 both has happened. Then the probability of A is actually 1, right? Because B1 and B2 both happen means that both are heads. So therefore, A is already true, right? Both flips are the same, is actually happened. So therefore, probability of A given B1 and B2 is actually equal to 1. So therefore, A is dependent on B1 and B2. So this says that, we can have pairwise independence, but mutual independence may not be there. So mutual independence is much stronger than pairwise independence. So we often require events to be mutually independent. Now, let us say that you are given a finite set, let us say T, right? And some number P is between 0 and 1. Okay. Now, I want to choose a random subset of T, which we call S. Okay. So S is a random subset of T, and I want to choose a random subset. Okay. So this could be, this could be also equal to, right? So this subset I can obtain, to get a random subset. What I can do is that I flip a coin, right? Every time, right? For each of the elements in T, right? So every element in T, what I do is that I pick the first element, corresponding to it, I toss a coin, right? If the outcome is a head, then I put this element into the set S. Okay? Then I take the second element, again toss a coin. Again, if it is heads, I will put it into the set. If it is a tails, I throw it out. Okay? So this way, I do for all the elements of T. Right? Then I get a set S, right? So this set S has the elements, whenever the coin toss was a success, right, which is a heads, then I will get the set, the elements in the set. So that set is a random set, right? Now, for each element, right, the probability is P for becoming a heads, right? Let's say in that case, we can use P to be any number between 0 and 1. If P is equal to 1, then I am always going to get the set, set T, right? And if it is 0, I am going to always get the empty set, right? But on the other hand, it is between, then you can get different set with different probabilities. So what are the probabilities of this happening? Well, when omega is basically what is omega? So basically it is 2 power T, which is the set of all subsets, right? That are the outcomes, right? The possible outcomes are the subsets of T, and probability of some set, right, which is a subset of T, is precisely probability of some subset S of T is precisely P raised to cardinality of S, right, into 1 minus P raised to cardinality of T minus cardinality of S, right? Which means that probability that these elements have been chosen with probability P, right, with success, and the other elements were not chosen with probability 1 minus P, right? Because if P is the probability of heads, probability of tails happening is 1 minus P, right? Whatever P is. So for all the other elements, it should have happened with probability 1 minus P. So therefore, there is 1 minus P raised to cardinality of T minus cardinality of S, right? So this is the probability of a particular set happening. Now, if S is actually equal to half, P is actually equal to half, then probability of S is actually equal to 2 raised to minus of cardinality, right? Basically 1 by 2 raised to cardinality of T for every subset of T, right? Because here half raised to this, and again 1 minus P is also half, so half raised to this into half raised to this, which is half raised to cardinality of T, which is 2 raised to minus cardinality of T, right? So for every subset, you have equal probability of happening, right? So that you can choose subsets of a set by doing this, right? If I have a pair coin, I can just choose any random subset for every set to happen, right? Including the empty set or the full set. All the sets has the same probability of happening, right? So this is a uniform distribution. Okay. So with that, we will now look at some applications of what we have learned to see how to help in counting or putting bounds. So we are going to look at some applications in combinatorics. So first, I want to look at a lower bound for Ramsey numbers. So if you remember, in our very first class, we looked at Ramsey numbers, right? So what was Ramsey numbers? So we have a complete graph on n vertices. Let's say the graph G is Kn, and we are going to color the edges of the complete graph with two colors, red or blue. So all the edges are colored with red or blue, and we want to see that, like, right, if I look at any subgraph basically induced by a subset of the vertex set, let's say S. Okay, so I take a subgraph induced by a subset of V. If all its edges have the same color, then when we say the subset is monochromatic. Okay, so G of S is basically the induced subgraph on the vertex set S. Right? So we have a complete graph. So we get again a complete subgraph. And this complete subgraph on cardinality of S many vertices, if all the edges of this smaller graph are all of the same color, it's all blue or it's all red, then we say it's a monochromatic subgraph. Now the question is that, can we guarantee, right? There is I give you a graph, right? I give you a graph, and then I give you two colors. You color the edges whichever way you want, right? Now I want to say that no matter how you are going to color, I can find a smaller graph on T vertices, right? I give you a graph on large number of vertices, let's say n vertices. Right? Then I ask, can I find a subgraph which is a complete graph on T vertices, where all the T choose 2 edges of this subgraph are going to be of the same color. It's all red or it's all blue. Can I find this? Now, the smallest n for which I can guarantee that this always happens, no matter how you are going to color, right? You can decide you pick each edge, color it, then you look at the graph, and then you find some subgraph which is monochromatic. You can change the color of that, right? You are allowed to do all this. Whatever you do, I say that, like, if my n is large enough, then I can say I can always find a monochromatic subgraph. If I can guarantee this, right? What is that smallest number which will allow me to do this guarantee? So that number is called the Ramsey number, right? So R of T is precisely the number which is basically R of Tt, where the way we learned in the first class. So R of T is the least integer such that, least positive integer such that every red or blue coloring of the complete graph on n vertices contains a monochromatic Kt. Now, we also said that, like, we found R33 is equal to 6, And in general, it is very difficult to compute for large numbers. For example, R5, we still don't know, right? R6, we don't know, right? So R5, R6, etc., we don't know, and we believe that it is not even feasible to really find it exact value. Then the question is that, can you find bounds for this? Like, can you say that it is there is an upper bound, there is a lower bound, etc., right? So here we are going to look at the lower bound question. So we want to say that, okay, can we guarantee that n is at least larger than some number? So this was proved by Paul Erdos in 1947 itself, right? This is one of the earliest applications, probably the first known application of probabilistic method to show something is possible or not possible, or some structure exists or not using probability. Okay. So here is the idea. Okay. So Erdos stated the following theorem. He said that suppose n choose t, which is the number of t element subsets of n, right? N choose t times 2 raised to 1 minus t choose 2, right? T choose 2 is the number of edges in a complete graph on t vector, right? So 2 raised to 1 minus t choose 2 times n choose t is strictly less than 1. Then the Ramsey number R of t is much larger than n. Okay. So the R of t is larger than n. So if this happens, then you cannot find you can always find a coloring of complete graph on n vertices where there is no complete subgraph on t vertices which is monochromatic. So you can always find a coloring like that. So and this can be reduced to say this, that R of t is greater than 2 raised to floor of t by 2, right? So it grows exponentially with respect to t by 2, right? So if t is growing large, then R of t grows exponentially large. So this is the claim that Erdos made, that the Ramsey number grows exponentially large, and here is the proof. So how do you prove this? So in any proof using the probabilistic method, we have to first come up with a setting and then a random experiment, right? So random experiment is the way to define the events and then the associated probabilities and things like that. So what is our random experiment here? So random experiment is the following, right? For each edge in the graph E, right? I mean in the graph G, for each edge, we toss a fair coin. So take a coin, toss it. If it is heads, then color it with red. If it is blue, color it with, if it is a tail, color it with blue. So probability of either the edge becoming red or edge becoming blue is actually half. So every edge has the same probability of becoming red or blue. So I take the graph on n vertices and do this, right? So this is my random experiment. So now because there is an associated probability for edge to be blue or red, I can define the probability space, event space, etc. Right? What are the things? So what are the objects that we are going to get? We are going to get colored graphs, right? So the graphs we are going to get are basically two colored, two edge colored complete graphs, right? Now suppose right, R of t is greater than n, right? Then Kn has a red or blue coloring that has no monochromatic additive. This is something that we know, right? That's by the definition of R of t. Now, yeah. So what is the idea? Okay. So the idea of the the probabilistic method is the very simple idea. Suppose you have, let us say that you have some numbers, real numbers x1 to xn. So x1 to xn are real numbers. Then I tell you that the average of these numbers is greater than or equal to a. suppose the average of some numbers I tell you is greater than or equal to a, then you know that for some j, xj must be greater than or equal to a, right? Because if every xi is less than or equal to a, I mean, is less than a, strictly less than a, then the average will be also strictly less than a, right? So therefore, by knowing that the average, without knowing, the number of numbers, without knowing any of the numbers, we can just say that from the average, we can say that there is at least one number larger than or equal to the average, or one number less than or equal to average, etc. Right? So here the average is greater than or equal to a. Therefore, I know that the one of the elements is at least a. Now, how does this allow us to use probability? Right. So the idea is that, like, if I can show that probability of something happening is strictly positive, right? It is greater than zero. Then that should be there, right? For example, I say that, like, probability of let's say probability of probability of, let's say, what example I can give. For example, finding a specific property, right, is strictly positive, right? Then I know. So what do I mean by the probability strictly positive? Right? Probability strictly positive means that, out of all the outcomes, right? These outcomes must be there. Otherwise, the probability of these outcomes will be zero, right? If at least these guys are not there, then I can never show the probability strictly greater than zero, right? Because, like, if you look at the what you call the discrete version of probability, basically what we are saying is that, you look at the favorable, right, events, and then divide by the total number of events, we can say that is the probability, right? So when we say that, what we are going to say is that probability is strictly positive, then, it should exist at least, right? So that is what. So we are showing the existence of something without actually finding it, right? Without actually telling you how to find it, we are saying that it should exist. So here is the uh, proof. So I define an event from our random experiment, right? So our random experiment was that for every edge, I color red or blue by tossing a coin with probability half. So I define the event as for a subset of 1 to n, right? The induced subgraph on S, right, G of S, is monochromatic. All its edges are of the same color. Right? That is the event AS. Now, what is probability of AS? Okay, if S has exactly t elements, then probability of AS is, either all the edges are red color, right? Which means that if all the edges are red color, then it can happen if the first edge, right? When I chose the first edge of the complete graph, it was colored with red, which has probability 1 over 2, right? So with probability half, the first edge was colored red. Then the second edge of this graph was chosen. That was also colored with probability half, right? Again, third edge, fourth edge, etc., right? Till all the edges of this complete graph. How many edges does this complete graph has? It has t vertices. So therefore, it has t choose 2 edges. So all the t choose 2 edges happen to be colored red. And what is the probability of this happening? Because we said that we are coloring each edge independently of the other edges. When I color the first edge, right, I toss a coin. For the second edge, I toss the coin again, but without looking at what happened before, right? I don't look at that before I color this one. So it is independent. So therefore, the probability of each edge becoming red is half, and probability of all the t choose 2 edges becoming half is the product of this. So what we are going to get is precisely 2 raised to minus t choose 2. But that is the probability all the edges are red. Now, of course, similarly, all the edges could also be blue, right? Since they are again, disjoint, we can add the probabilities. So, probability of AS is 2 into 2 raised to minus t choose 2. So, for the event AS, that is a subset on S, subset S of vertices is monochromatic, is 2 raised to 1 minus t choose 2, where t is the cardinality of S. Now we can use the union bound, right? So if you take the n element set, right, which is all the vertices, and look at all t element subsets of this. How many t element subsets are there? N choose t element subsets are there, right? For each of the t element subset, I know that probability that the complete subgraph on that subset becoming monochromatic is 2 into t raised to minus t choose 2, right? So, what is the probability that at least one of these t element subset is monochromatic? That can be upper bounded by the union bound as the sum over all the events, the probability of the events, right? So, sum is going to give you like n choose t because there are that many subsets, and for each subset this is the probability, right? So therefore this is a upper bound. It's a bad upper bound, but it is still an upper bound, right? So it says that probability of all this thing is less than or equal to n choose t into 2 raised to 1 minus t choose 2, right? So the probability that at least one of the t element subgraph is monochromatic is less than or equal to this. Of course, there is lot of intersection, and therefore, this bound is actually going to be even smaller. But we don't care. We are saying that it is still an upper bound, right? Because union bound says that sum over all the probabilities is an upper bound for the union of all the events. So therefore, we show that probability of the union of AS is less than or equal to n choose t into t raised 2 raised to 1 minus t choose 2. Now, by the assumption in the problem, this factor, right, this number is less than 1, right? Strictly less than 1, right? So if it is strictly less than 1, then probability that this event does not happen, the complement of this event, right? Probability of union AS does not happen is strictly greater than 0, right? So this is our assumption that we had, right? And from this we know that probability of the complement of this event is strictly positive, right? Probability of intersection AS complement, okay, there is a complement here, right? Which is 1 minus probability of union AS, right? This is the complement event, and that has strictly positive probability. What does that tell us? So what is the complement event? The complement event is that AS does not happen for any subset S, right, of cardinality T. So for none of the T element subsets, the complete subgraph is monochromatic, right, with positive probability, right? So therefore, at least for one of the colorings, we should not be able to find a complete subgraph on T vertices which is monochromatic. So for that, we have strictly positive probability because of that. So that is what we wanted, right? So there is some red or blue coloring of Kn with no monochromatic. So this tells us that there is, so if n is less than if n is such that this happens, right, then there is such a coloring. So which means that R of t is greater than 2 raised to t over 2. Why is that? Well, that is something that you can derive from the fact that n choose t into 2 raised to 1 minus t choose 2 is less than 1. Using this approximation for factorial, like k factorial is greater than or equal to 2 into k by e whole raised to k. So this is something that is given to you. So use this, and the earlier assumption, and then show that from this we can say that the Ramsey number, right, R of t is strictly greater than 2 raised to floor of t by 2. Okay, so this is a homework for you. Okay, so is that clear? I hope if there is any question, please feel free to write to me. Now, we will look at another example, which is list coloring. So one of the reasons we introduced graph theory was to look at this kind of question. So given a graph G, okay, so you all remember what is the vertex coloring of a graph, right? So what is the vertex coloring? Every vertex must be colored with some colors, like some numbers, like 1, 2, 3, etc. up to k maybe, right? And then we are asked to make sure that whenever two vertices are adjacent, connected by an edge, they don't get the same color. They are given different colors. So this is called a proper coloring. So graph coloring question asks to find a proper coloring. And then the question is, what is the minimum number of colors that will allow such a coloring, right? That is called the chromatic number. Now, in this, in the graph coloring, we said that we are going to color with the set of colors, like some k colors, which could be always like the set 1, 2, 3, etc. up to k, right? We are because name of the color does not matter, so we can assume that the set is set 1 to k. So once you start with the set 1 to k, I am basically saying that every vertex has any of these colors available, right? Like 1 to k is available to all the vertices. So I give the set 1 to k to all the vertices and say that, okay, color using one of these colors, right? So this is called the vertex coloring. Now, instead of this, suppose I say that, okay, for each vertex I am going to give you a different list of colors. So the first vertex I will say you can use the colors 1, 2, 3. For the second vertex I will say you can use 2, 3, 4. And another vertex you will say you can use 3, 5, and 7, right? So this way I give you different sets of colors to each vertex. Now I ask you, can you color the graph with this colors, right? Now suppose I say that I will allow you to use k colors for every vertex. So every vertex will have exactly k colors associated with it, right? So like first vertex has 1 to k, right? Second vertex has 2 to k plus 1. Third vertex has 3 to k plus 1 and maybe 5. I mean and minus 1 or something like that, right? Some numbers, whatever numbers. So you will always have k colors with each vertex. Now, the question is that does it make the coloring easier or more difficult, right? In the sense that, see, suppose I give every vertex the same color, right? Same list of colors. Now, if I look at one vertex, I look at a color and use it here, then in all the neighboring vertices, I cannot use this color, right? Because all the vertices has this color, so I cannot use this color. But if I give a different list to the neighboring vertex, right, then maybe I can use the color that is not used there here, right? I mean that is not present there, but so this list has 1, 2, 3. That has like 2, 3, 4, right? So if I use 1 here, then it is not going to make any difference to the list of that other vertex because it still has 2, 3, 4 available because I have 1 is not there in its list at all. So one can feel that maybe using different sets of colors on vertices makes the coloring easier. But that is not always the case. Okay, by giving different sets of colors, we can make it more and more difficult for coloring graphs. So we will see this why. Okay, so let me define list coloring more formally. So every vertex of the graph is associated with a list L of V of permissible colors. Okay, so whenever I want to color the vertex, I have to use one color from its list. Now the list coloring aims to assign a permissible color to each vertex so that adjacent vertices again get different colors. Okay, so this is called list coloring problem. So list coloring is a generalization of vertex coloring, where now we have constraints on the colors. Now, suppose I tell you that the chromatic number of the graph I am going to give you is let us say 2, right? Which means that if every vertex is given the colors 1 2 1 2 1 2 1 2, right? Then I can color the graph with just these 2 colors. Right? So such graphs are bipartite, that we can see, because if I look at all the vertices of the same color, they form an independent set. All the vertices of the color 2 is also an independent set. So I have a partition of the vertex set into 2 sets which are independent. So therefore it's a bipartite graph, right? So right, so I look at a bipartite graph, right? Bipartite graphs can always be 2 colored. But now I say that, okay, instead of giving 1 2 1 2 to every vertex, I will say that, okay, for one vertex you use 1 2, second vertex you use 2 3, third vertex you use 3 4, right? Or 1 3, whatever, right? So this way I give you different sets of colors to each vertex. Now I ask you to color this. Can you do that? Okay, so maybe you can take some graphs and try it before you look at further. But oh, I show that this can actually change the I mean it can make it difficult to color the graph or impossible to color the graph. Now, what is the least chromatic number, which is the least k, such that I guarantee that every vertex has at least k colors associated with it. Whatever the colors are going to be, I will say that you will always get k colors. Right? Now, can you color it? Right? So the least coloring number is basically the smallest k such that if I guarantee that L of V is greater than or equal to k for every vertex, then you can always find a coloring where the color comes from the associated list. Okay. So such a proper coloring from the associated list. So that is called the least chromatic number or the choice number of the graph. Okay. So the choice number is the smallest k, which will guarantee that if I give you every vertex has at least k colors, then I can always find a color. So this is usually denoted by either chi L of G to say that it is we are looking at the least chromatic number, or choice number of G, because we are basically saying we are basically choosing, right? Like so this is more general, because what we are saying is that no matter what lists are given, I should be able to guarantee this, right? See, it's not for a particular given list, right? So I give you the number k, and I say that, okay, I give you right, like the freedom to choose whatever list that you want, right, for each vertex. I will say that, okay, if you give me at least k colors on each vertex, then I will be coloring whatever the list that you are going to give me. So that is the guarantee. Okay, now one observation is that if right, this is something which we already mentioned, that if all the vertices get the same list, right, 1 to k, then it is the problem reduces to finding the chromatic number of the graph. But when these lists are not fixed, then it is the list coloring problem. Now the surprising, maybe not surprising for everybody, but it could be a kind of not trivial to immediately see that the choice number is greater than or equal to chromatic number. But why is it actually trivial? Because even though it is not intuitively clear, maybe it should be clear why this is greater than or equal to chromatic number. Because I can always give the list all to be the same, because I have the freedom to choose the list, right? So if in that case I have to need at least the chromatic number of many colors. Right? So that is necessary. So therefore, choice number is greater than or equal to this, but it happens that it can be much larger than the chromatic number. So we will give you some examples for that. For example, you take the bipartite graph, which usually can be colored with two colors, right? That is why it's bipartite. I associate the following list 1, 2, 1, 3, and 2, 3 to these vertices. Again, 1, 2, 1, 3, and 2, 3 to the other vertices on the other side. Now the question is that can you color this graph, right? Can you color this graph with this list assignment with just two colors for every vertex? So the answer is actually no. Okay, maybe you should verify this yourself, but I tell you how. Right? Suppose I give you this coloring, then I have to color one of these vertices, right? So maybe I start with coloring this vertex from its list, let's say using 1, right? Now if I use the color 1 here, then I cannot use color 1 here and here also, right? Because it is neighboring these two. So therefore, if I use color 1, I am forced to use color 2 here and color 3 here, right? Now if I use color 2 and 3 here, I cannot color this vertex, right? Because that vertex has only two colors, 2 and 3. But 2 is used here and 3 is used here. So therefore, I cannot do. If I start with color 2, color 1, I cannot do. So therefore, I can say that I definitely need to use color 2 here. Right? Now suppose I use color 2 here, then color 2 cannot be used here and here. But then I have to color this with 1 and this with 3. Right? But then this vertex is colored, it has choices 1 and 3. But 1 cannot be used because 1 is used here. 3 cannot be used because 3 is also used. So if I choose 1 here, I don't have a coloring. If I choose 2 here, I still don't have a coloring. Right? So therefore, I cannot color with this list at all. Right? So there is a list for this bipartite graph where every vertex has two colors, but still I cannot color this. Now it happens that we can make the chromatic number of the bipartite graph large enough. If the bipartite graph has larger degree, we can make the graph has chromatic number as large as we want, right? By increasing the degree. Okay. So this is something that maybe you should think about it, and then we will continue in the next class on how to go further from here.